how can I apply AI here? Or how can I apply chemistry here? So how can I apply, this translate into some, useful findings for the industry? Basically, I am an industry man. So currently I'm doing, my job in rubber board was to look after around 10,000 factories all over India. They are making a lot of products, testing, specification testing. Then give a report. Based on the report only, they can market their product. So we have an NABL accredited testing laboratory. And if that test failed, somebody came there and tested their product. For example, that the nearby factory, St. Mary's, is coming there for testing the surgical gloves. And there is a specification for that. With that specification only, they can sell this to a hospital. Otherwise, it is a highly regulated product. They cannot sell. Otherwise, if there is any shortcoming there, then they will suffer severe. They will face severe problems. So there is checking and the auditors are there. And when they come there for their product testing, for example, surgical gloves, they have has around, I think, 16 specification testing, starting from the thickness. The thickness is, it is written, how much is the thickness of a surgical gloves, approximately? How much? It is 0.18 mm. So depending upon different, don't believe that there is only one specification. And in India, we are mainly dealing with the specifications. So there is a specification dealing body in India. I think, what is that one? Specification Authority of India. In our pressure cooker, it is written. BIS, Bureau of Indian Standard. Bureau of Indian Standard. They regulate all our specifications. And everybody cannot raise, that their own specifications. Only BIS has to approve. Suppose we find made a good invention, and you cannot test that product as per your wish and will, and then cannot sell that one. It has no legal sanctity. So what we have to do, if it is a good test, you refer to what is called BIS. They will check this one, and then if it is related to rubber, they will send it to us. If it is related to electronics, they will send it to some of the central authority of that electronic department. Or if it is a metal, then concerned department. Then they have a series of discussions and meetings. Then they will approve whether this method is suitable for the concerned sector. Then only they will approve, and then your method will be a good testing method. So that is the way BIS is devising different testing method for different type of products. So once you test the product, suppose the test fails, that for example, the surgical gloves here, I said surgical gloves because probably you might have visited this one. And for example, tire again, the tire of car, and it's a tread. A tread has around 22 parameters to test first, the abrasion resistance, its hardness, the compression set, everything you have to test. And there is a limit for everything. And if the exceeds a limit, lower limit or upper limit, then it is not qualified. The entire things will be, they cannot sell that product. So our duty is to then again redesign the formulation. So testing, development, and then innovation. We have an innovation center also there, and some 22 innovative projects are running there. So that's all about our work. And mainly, so I suggest, all of you sitting here, whenever you deal with your curriculum or research or some type of work, go to the concerned specification. Everything has a specification. For example, somebody is doing AI, you check with which is standard guidelines to use AI. So ask AI itself, then AI will give you what is a guideline. So there is a guideline and a specification. You have to go only through the guidelines in all testing. Otherwise, whatever you are doing is probably wrong, that you may understand at the final stage. And people will understand from this your thesis, and then this is a useless work. So we will make a conclusive idea about that. So I suggest, because I also don't know about in your age, I don't know this one. So I did a lot of mistakes in my testing and in my thesis work. When I became the part of the BIS, and later I am the chairman of the BIS, So we know how important these tests are, and nobody is following this one. So that is why whenever you make a swelling test or tensile test, even for metal, even for a tensile for a rubber or plastic, or whatever may be, breaking strength, you go to the concerned Indian specification and also IS specification. And don't believe that the specification is only for IS. And India, that is a Bureau of Indian Standards, and their specifications are known as IS. Whereas if you want to market some product, your product in America, their specification is, what is American specification? ASTM, then Japanese, yes, then so, and again European countries. So you look at that. So when the product comes there, it is as per EC, European Union, EU specification. So everywhere there is a specification. I think over 100 specification bodies are there, and we have to test like that. If you suppose you are making a tire here and you are exporting this to Russia, the Russian room temperature sometimes go down to up to -40, whereas our temperature is 30, 35. Then polymer, the major component of the tire, is sensitive towards the environmental temperature. So it may be glassy there, abrasion base very high, slipping away from the road. So we have to test the recent specification here for exporting a tire from here. So that is a thing also. So not for Indian specification. So how can we do this one? But how can we do Russian specification here? We don't have facility and knowledge about the testing the Indian specification. How can we test a Russian specification? Then go to the accredited laboratory. They have all procedures. They have all instruments, and they are aware of this one. So that way we can, make your product and test your product. This is not only for industrial people. This is true for the people like you who are doing engineering and research and other activities. We should be aware of all testing procedures and download the specifications and read it very well. So then only your data is valuable for some industry. Then coming to that one, then again. See, I said, that sometimes my talk may not be that much interesting for you because it is fully related to rubber. For years, I am sitting with rubber. I know only rubber. So I forgot all chemistry. After MSc and some courses, I didn't handle a beaker or a burette. So the expectation may be different. So maybe teachers from colleges is expecting something, but I'm a fully an industrial man dealing with the rubber products and specifications and factory setup, and that's the thing I'm doing. So, but I can translate. I can give some idea which you can translate. Okay, then even in between my talk, if you have some small questions, please ask. Then I can orient my talk accordingly. I usually never stick on to my slides. This is a slides I talk everywhere, but I never stick on to that one. So I will talk something peripherally. Then you can respond immediately. You can ask even Malayalam, no problem. I will respond to that one. I also like Malayalam very much. Then coming to the things, see, when I say nanocomposite, this is there are some terms, can we use nanotechnology in some products in metal or rubber or something? Of course, nanotechnology is slightly expensive, and that the metals, when you heat the metals and cooling, then something happened to the metal. Metal is very stiff and there is no material change. Material is still iron. It is what is called the atomic number. There is no material change, but material property is changing. And it is now says that, it is undergo fibril, orientation. Because the ancient swords, which unbreakable swords are made up of this type of annealing and heating process, which are unbreakable. So that is nanotechnology. That they are using that word, but that time, but the explanations are all coming now. So don't think that this can apply only to rubber. So wherever we want to apply nanotechnology, make sure whether we need to apply that. So for example, I said, that nanotechnology can be applied in surgical gloves. Surgical gloves, the purpose is to protect the doctor from, pathogens and viruses protect. That's the idea. So they use it and throw away material. It is a premium product. Can we use nanotechnology there? Oh, okay, sorry. Okay, sorry. So I'm asking where we need to apply nanotechnology, because you know that in rubber people are asking when the nanotechnologies emerged as a new science. People are asking, can I use, all the factories want to use nanotechnology. Even the rubber mat people want to use, you know, that washer making people want to use gloves, tire technology, everybody they want. Then it is a scientist who want, you know, decide whether we can apply there or not. Anybody can apply. But the problem there is these are expensive materials and we need to look for some property, enhancement of some property. If your nanomaterial can contribute to that particular property in that product, then we can use it. For example, natural rubber is it flammable or flame retardant? It is a highly flammable. So can we design, you know, then we cannot use natural rubber in, you know, flame retardant applications. And somebody, if nanotech, somebody is asking a fire retardant tire, no, then we can apply. There is a process for that one. There is some material available for fire retardant tires using nanotechnology. We are coming to the applications of this one, then we can see. So that way, then whether the thing is our ordinary surgical gloves, it is going well now without any nanotechnology. That the product is running smoothly in the market. Then all of a sudden, you know, the owner, the promising owner is asking, can we apply nanotechnology? Will you recommend this one? Can. Then we have to ask, what is your application sector? Are you using the common, what is called the, you know, conventional hospitals, or you want to treat with some new viruses, maybe for abroad or UN something, you want to export this product because this is expensive. So what are the advantages? You will get some strength advancement, especially the barrier properties. Natural rubber has small holes, even the films. That is why inner tubes we cannot make with the natural rubber. So we have to seal that small molecular level holes so that the virus can penetrate through that one. Then we can, if we can seal this one, it is good, but it is only for very, very small viruses. So most of the viruses, you know, normal gloves can prevent. Then why we need to use this one? So only to premium products and only in some isolated areas and only in areas where the producers, the manufacturer can get premium prices, only we recommend this one, not to all products. So that way we have to check, you know, these are some of the, I think all of you know this one, the tensile strength increases, barrier properties, solvent resistance, submersibility, flame retardants, and you know, which is a major superior property which we can achieve with the, can you tell me, with the nanomaterial? One or two, high strength and good flame resistance. And it is not for rubber. I'm not talking, not limited my talk to rubber alone, all materials. It is strength and flame retardants. If it is a polymer, it is flame retardants. If it is metal, strength. So that way we have to screen your application, then you can select your nanomaterial. I think, you know, this is how many of you are familiar with these things? Just raise the hand, I want to know. So probably some people are very new to this. So I have to introduce this to them also. There are three types of nanomaterial. Nanomaterial can be classified into several ways. We can classify. And then the simple classification is based on their sizes, one-dimensional, two-dimensional, and three-dimensional. Means that is why we have three dimensions. Why only three? Because there is length, breadth, and height. That way we can characterize the material. So the length, if the thickness is small, then it is a one-dimensional nanomaterial. That is a clay, ordinary layered clay, graphene, and everything comes under that one category. Then Then 2 dimensions are in the nanometer range. Then carbon nanotubes, viscous, these are all in the middle category. Then if all the material, all the dimensions are in the nanometer range, that is nanosilica, for example, very fine powders, very difficult to handle this material in the industry because of fluffy powder, lot of problems we are handling. So these are the category, 1 dimensional, 2 dimensional, and 3 dimensional. And in our major discussions and applications may be limited to 1 dimensional and 3 dimensional materials. Say I said, when we had one, in our technology and polymer technology or in metal, when we replace the conventional technology with the nanotechnology, we are adding, either you can modify the base mother material like that, or you can add additives into that one. For example, if you add nanosilica into the rubber, the reinforcement is very high. For example, normally we are adding, conventionally, why a tire is black? Because we are adding carbon black into that one for reinforcement. That makes rubber more strong. But for that one, for getting appreciable amount of what is called abrasion resistance, then you need to add around 60 to 70 pHr of carbon black into that one. And remember that only 40% is rubber. Then what happens? The rubbery property of the material will go down. It is not at all a polymeric material. It is a non-polymeric material because the major component is something else. But we need to add that one to get the desired property. Then can we reduce this one? 60 to some 10, 20? Can, but the property never meet. The same is the case with the silica. We are adding 20 to 30% of silica in rubber compounds and most of the rubber materials to get the desired level of hardness and abrasion resistance, which is designed, designed in the specification. Then the problem is mixing problems, and the property, elastic nature of the property will lose. Then if you use nanosilica in that one, 1 or 2 pHr of nanosilica will solve the problem. Normal silica 30 pHr means approximately for 100 gram of rubber, you have to add 30 gram of rubber silica. For every 100 gram, 30 gram of silica. For in the nanosilica, add 1 or 2, 3 maximum. So what is the science there? Then you have to learn what is the science there. For that, I can explain this with this one. You can see that here, see, we have a reference volume of this much with 50,000 micrometer. This is a reference volume, 50,000 micrometer, and we have to fill it with the 3 volume% of the material. And we are loading only with the normal material with the diameter 10 micron. Most of the fillers adding in the rubber technology for polymer are in this range, 10 micron range. For zinc oxide, China clay, silica, carbon black, all are at medium 10 micron. Then if this is a reference volume and you are adding to 3 volume%, and this is a diameter, you can only incorporate three particles in that one. Then see, most of the polymer materials are not in contact with the filler. That part is weak. So that may eventually go to the product failure. Then coming to the next one, there is the same area, 50,000, same volume area. And then we have to reducing the dimension of this particle to 1/10 of that is diameter 10 micron to 1 micron. Then we can incorporate 300, almost 300, 2,860 particle in that one. And there is no volume change. That is the thing we have to make. Then again, in the final, we are reducing again 1/10 of this one. 1 micron is 1000 nanometer. So this is 1000 nanometer. And again, reducing that to 100 nanometer. Then you can see almost 3 million particle in that one. This is a nanotechnology, and this is a microscience, and this is in between. And most of the time, we are only going up to this level. We cannot, because of certain problems, unknown, difficulties, we cannot reach fully to this level. This is actually nanotechnology. Then how much is the thing here? You see the volume change. What is the science behind that one? I said, you know, you can fill, but what is the science in that one? How we can get, for example, suppose here, suppose 1 megapascal is your tensile strength. Here you will get 1,000 megapascal. So what is the science in that one? Which factor is playing there? Surface area. This huge surface area generated this one. And can you tell me an organ working in our body with nanotechnology? That is our lungs. It is very soft. It is made of fully small capillary tubes where our bloods are passing. Then, you know, blood is passing and then oxygen diffusion is going on. And blood is going through that molecular thickness. Then only can communicate with the oxygen. And if you cut every vein, capillary veins in the lungs, one over another, and it's safe, you can cover entire roads in India. That much things are there. So surface area is playing here. Then I said, you know, that we are one-dimensional, two-dimensional, and three-dimensional materials mainly. And in nanotechnology, there are a lot of dangerous materials are there. And generally, we won't work within laboratories and in rubber board and other things. Our programs are not fully academic. Our programs are industrially oriented. So we cannot promote something hazardous to the manufacturing people, because if you can take nano silica, you have to deal with the glove box. So it can be such a fluffy powder, and if you inhale, a lot of problems there that nobody can identify, and nobody can prescribe a medicine for that one. There are a lot of cases, court cases are going on abroad. Student filed against professors. So we always, deal with, material in the liquid state, because we make sure that nothing will come out. So that is why we normally select this type of one-dimensional material. All these are basically clays, layered silicate, and as such, this material is micro material, not at all nano. When we disperse this in suitable medium, solvent, monomer, or aqueous medium, they will convert. And then we will do entire thing in situ, so that the process will be harmless for the manufacturing people and the handling people. And if the student is unaware of the process, where the professor is away, you have to be very careful, especially when you are dealing with what is called carbon nanotubes. Very, very hazardous material. Modulus is very high. When you put it into the rubber, it will eject like a bullet, and it may stuck your skin, and lot of problems. So because the modulus difference is very high, it won't adjust in the rubber system. So we won't recommend this in the rubber, in this one-dimensional nanotubes. So there are other materials which are suitable for this. These materials are suitable maybe for some other material. Rubber is rubbery, it is elastic. So when you stretch it, the non-wanted loose particle will eject, especially if the modulus is very high. So whenever we handle these materials, we be very careful about putting 2-3 gloves and mask and glove box, whatever precautions you can, please do that one, especially in the solid state. Then, so what are the advantages here? I said, again, in nanotechnology, the surface area is playing. Surface area means 700 to 800 meters square. So normal nanotechnology, normal clay is China clay, precipitated silica. These are all silica category. How much is what is called the surface area? Which we need to add around 30 to 50 parts in normal polymer systems. It's 80 meters square. You can see that 80 meters square is almost the area of a football ground, remember. 40 meter into 40 meter length and width, that much surface area is playing in the polymer. So then you come to the 10 times of that one, you can reduce the dosage. So that is idea with this cation exchange capacity. Then lot of silicates. I'm not going into details this one. These are some of the minerals which they play, where I want to say that the interstitial ions, some of the ions also play some role here. They say how the clay is made up of, there is an, silicon tetrahedron, and then magnesium lithium octahedron is fused between two silicon tetrahedron, where rubber is going in between. This is one silica sheet. This is another silica sheet, and the rubber is going in between so that it is reinforced. And the strength of this silica, is almost 178 gigapascal. It is stronger than steel. That is the idea. Reinforcement. Why this? In normal occasions, this space is too small. Rubber cannot or polymer cannot penetrate. So that is why nanoclay is working very well in these systems. See, this is some of the idea. This should be in your mind when we deal with some of the applications later. So you can see that this is a polymer. This is a clay layer. This is a clay layer. It is coming in between. And finally, the relaxation of the polymer will be destroyed and it is disrupted. And their chain will be disrupted. So we have some terms called intercalation and exfoliation. So these are some of the terms used in nanotechnology. In later applications, I will tell you what are the advantages with these systems. And you know that when you mix with rubber, this is not to look into this. Never think that, oh, this I have seen 100 times, but it's useless, this one. Don't think like that. When you mix with a polymer or a metal or any material, so we have two systems. And if it is not undergoing the desired change in the material, we think that they will make a bond. For example, in the carbon black, when you mix it with the rubber, there is microporous cavities in surfaces of carbon black, and rubber will penetrate into that one. That way, it is called occluded rubber. So that will give the reinforcement for the tire. And it is not happening, then this material will look like, appear like this one. The rubber is somewhere else, and the polymer will be there, but there exists as separate entity. And there is no interaction, of course. In that case, need to add lot amount of material because we have to wet entire polymeric material with the fillers. So probably we need a 60 pSr. Then in the next one, some amount of interaction will happen. Some of the polymer will penetrate, and that is an intercalated structure. Then we can maybe reduce the amount of material to half of that one. And finally, this is the exfoliated state. The entire thing will be polymer. Every polymer molecule will be in contact with the reinforcing material, just like we are reinforcing concrete bars with iron. That very concrete is very hard, ductile. But it can't stand like that because for that one, we have to put steel into that one. And we are putting entire steel there and there is no steel here. So that part will collapse. Same is the polymer itself. And for example, look at the tire, the running material. So how much is the weight over that one? Can you think of that one? 4 tires, how much it tons, and especially in heavy vehicles. So the construction is something, difficult to imagine. So it is resting on that one. I'm running it is a dynamic application. And there are two types of application in science, static and dynamic. For example, you are putting a mat on a floor and you are walking over that one. It is a static product. It is not moving. Whereas your tire is rotating, it is dynamic. So whenever you do testing, we will take care of this one. And tire is tested in the dynamic stage. And mat is testing in the static state. That is why whenever you go for a specification with the product, you have to tell whether you need a dynamic test or a static test. If you did vice versa, then the test report is not valid for that particular product. You did the product, you did an entire job, but the product is not representing that particular test. So static test. So how can we do a static test? Can you tell me a static test? So I think people sitting here, we are testing rubber or we are testing a steel wire, tensile, modulus. So clamping two ends and pulling apart and breaking point, you will get it. Is it a static test or a dynamic test? We are stretching this one. So is it a static one or a dynamic one? Dynamic or static? It is static test. It is not dynamic. Then where is the dynamic test? Can you tell me one instrument doing dynamic test? I think a lot of people use this one, but you are not aware of this one and not listening that because you are not, read the specifications. Specifications, it is written that when you go for this type of test, it is dynamic. So for example, dynamic mechanical analyzer, we are measuring frequency, modulus, and everything there. That is DMA, dynamic mechanical analysis, where the sample is vibrating. Sample is vibrating the same frequency as that of a running tire. A 12 hertz frequency we are doing for a dynamic test means 60 mileage, 60 RPM for a running car. So we are stimulating the same condition with the instrument. So without knowing this one, so you know that when we do the thesis work and everything, you know that we are looking for that what is called this frequency of the material testing. We can see that you can select any frequency, 3 hertz, 5 hertz, 10 hertz, 100 hertz, 50 hertz. And people are using without any sense that one. And he is testing, he's doing some research work in the tire shed. And the ideal frequency test is 12 hertz. This is equivalent to some running speed of around 60, that miles per hour. So imagine this type of things are there. So then when you make your product and after completing thesis, you're approaching some of a lot of translation works are going on. I want to put my work into industry and nobody is approaching us. My product, I got a Young Scientist Award and I published so many papers and my paper is #1. But nobody is responding to my thesis. The tire man already read your paper and he understood that you did the wrong test. And you are declaring that product is wonderful for the tire. Instead of 12 hertz, you use the 3 hertz and 30 hertz. So this is the things, you have to be familiar with that is why your data, because you are capable of doing good work. We have facilities and there are people, scientists and supervising teachers, they can interpret the data, but it is not the problem of the guide. Guide has several students and has teaching assignment. The student has to go deep into the specifications and all things understand. And that way you have to lead. Then only your PhD work we can translate into the industry. Same is the case with the lattice industry also. Even for the rubber mat, it's a simple product. There are a lot of specification tests we have to do carefully. See, I think I'm not going deep into this one. I think you are all familiar with this one. These are the different preparation route for nanocomposites. And we are mainly dealing with the lattice nanocomposites. Lattice is actually a rubber dispersed in water. So we are adding nano dispersions into that one so that it is a friendly process, not a harmful process. Then we are giving some identical conditions so that the rubber can penetrate in between. Then we are doing the normal process. This you can do in several ways. If it is a dry rubber, dissolve in a solvent, then do the things. But whenever you select the material what I am going to stress here, that whenever you select rubber or polymer or a material for your research work, you have to join the identical material. So, for example, here see the things. There is a pristine clay, means the pure clay, and modified clay. What is the difference between these two? Most of the thesis coming for evaluation, people don't know this one. And and we usually question this as the what is viva voce and the final stage. What we want to do, because that is the final stage. If you make any negative comment, that will affect the student. But if you didn't make anything, the whole people sitting there will follow the same trend, and this will be multiplied. So that is why I'm telling you have to understand the basic differences. And then this one, the pristine clay and the organic clay. One is modified. This is pristine is, we have mined the clay, purified the clay as such without any modification. It is soluble in water. And in some of the cases we are do dry rubber mixing, dry rubber polymer mixing. Then we cannot use this one because this is this dry rubber mixing. Dry rubber is an organic material, and this is more or less inorganic material. There is a compatibility problem. So then you have to use it. You have to make some adjustment with the clay, becomes more familiar, more suitable for the rubber, adding some rubber flavor into that one, adding some monomer in between the clay, that is organic clay, modified clay, so that it can be easily mixed with the rubber in the dry state. What is the problem? Suppose I'm adding pristine clay into dry rubber clay, what happened? Knowingly, unknowingly, I am adding pristine layered clay into a dry rubber system. Or I am adding an organic modified clay into latex. What happened? Then I will show what happened. Go back to, you will end up with this property, this one. Because you selected your materials are ideal, expensive material, but you selected in a wrong way. And you are saying that, sir, my clay is not good, or my process is not good, whatever I adopted is wrong, so I'm not getting property, you will change the material. But actually, what happened is, that you selected in a different way, so the raw material should be matching each other. So means organically modified clay is organic. It won't match with the aqueous medium. That is why when you add kerosene into water, what happens? When you add kerosene into water, separation. Same system will happen if you do this one. These are the two independent routes here, and these are the two independent routes here. There's only one common route both for this one. Only that way we can approach the final composite. So selection of the material is very important. In any research programs, and this is very important, not for other. So selection. How can you do this one? Literature survey and look at the property. Wherever there is a property advancement, then you can click that one. That method is correct. Then go there. And even nobody will spend that much time for you. So that way you can pinpoint the correct materials and process. This is a layered silicate modification without, see the modification. I think you know what is modification. Modification is just lifting the layer in between the layer distance so that the polymer molecule can penetrate. We are putting some monomer there, and you are increasing the things. This is on the nanometer range. For example, the ordinary clay, China clay, this distance is around 0.71 nanometer, 71. For rubber penetration, we need a minimum 1 nanometer or 0.9 nanometer. So this will work as a normal clay in polymer, whereas if you modify this one, it will work as a nanomaterial, because copolymer can penetrate. That's a science telling here. There are a lot of things here, but I'm giving the slides here. You can study, and if you have some questions and things, you can write. I said, that is very clearly you can understand, that this is a normal clay and there is no modifier, and you can do the distance, Armstrong. What is the difference? Relation between Armstrong and nanometer? which is, tell me, one Armstrong is how much nanometer, or 1 nanometer is how much Armstrong? Yes, once 1 nanometer is 10 Armstrongs. So you can see that this is a 1.1. Sorry, this is 1.17 nanometer or 11.7. And then that what, then when you put, material in between, depending upon the size of the modifier, the distance will increase. And again, in rubber technology, there is a big problem. And those people doing research in rubber technology, you have to be very careful about this one whenever you select the clay, because see this clay, this modifier. Can you tell me, look at and tell me, are they basic or acidic? These materials, generally, is it acidic or basic, this material? These are basically basic, generally basic. And what in the rubber or in the polymer system, we are adding an amine for accelerator system, accelerating the vulcanization process with the sulfur. For example, TMTD, zinc oxide, ISADC, there are several accelerators. And what happens if you add any of these one to tri-rubber system, this will act as a accelerator. And entire thing, whatever you put for the clay here, this is your modifier. This is a basic system. When you add this into the rubber, what happens? This will come out of the rubber, the clay, and take part in the vulcanization reaction. And this will collapse. The rubber will collapse. The clay will collapse. So you will not get a nano. It will be a microcomposite. You have to be very careful about this modifier in the clay, and you have to select a acidically modified modifier for the clay, for the dry rubber system. That's it. So this is very important. Then I said, that there are different systems for making these nanocomposites. Some maybe pictorial representation is more easy. You can see a clay and then monomer putting in between, then more polymerize the system, you will get a nanocomposite, or you can either directly force this material in between by milling process, or you can put a clay dispersed in water. Then it should not be a modified clay. Modified clay will not disperse in water. Why? It is organic. Kerosene water system. And then if this is a correct system without modification, latex, then add this one, you will get the nano. So that is selection of raw material is very important in rubber. These are the same system I said, Then I think, that the characterization is very important for nanomaterials, characterization. Unfortunately, most of the characterization techniques adopted for nanocomposites are very expensive, and we need thorough checking, instrumentation. And these are the major tests, main tests. Whether a nano is formed or not, we can check. Whether your composite, you added the right materials, nanomaterials, expensive, did the correct procedure, and tested. And you didn't get the desired properties, modulus, enhancement, or abrasion resistance, use any of these process, whether nano is formed there. And that's the X-ray diffraction technique, differential thermal analysis, electron microscopy, and infrared spectroscopy. And the X-ray diffraction, I think this is people are doing in metal also for crystallinity, defects, and other things. Suppose you want to do either X-ray diffraction of a material, polymeric material or metal, what will you do immediately? What is the process procedure? You want to do them X-ray, you have to record. Your guide asked you to, your teacher told you to make X-ray diffraction of the material. He said only that one. So what we need to do, cut a small sample, send it to your friend and do it and check the things, whatever he wrote, you copy this one, put it in the thesis. That is not the method. That's the same method we adopted in previous cases, end up with a lot of problems. The thing is, you go to the, it's a very simple method for testing X-ray diffraction, method for testing X-ray diffraction of polymers. Put it in the chat GTP. You give you a right, which is ISO governing that particular test. What you should do, what you should not do, they are telling. How much is what is called a specimen size, how to prepare that one. Their thing. What are the environmental conditions when you do this one? Everything is written there. I think sometimes it is a 30-page write-up. You have to study that one. Very important. And you have to record this number in this is a test I did. So for all this analysis, first go to the specification. What are the advantages? What is advantage? You need to refer a specification test. You can get even maybe the second phase of your research. They are telling that this may be good or that may not good. Then you can do research on that area also. The specifications are based on thorough research by developed countries. And in India, we never developed any specification test. We are adopting ISO, International Standard Organization test. And it is based on several factory and R&D process they designed it. And every word of this one, the sample is, or in the sample was, everything, everywhere is there put, designed after a thorough discussion, because I'm a part of that one. And they take even hours, night for discussing this one. So that is more useful for us. So whenever you go for this type of test, go to that specification test, read it. And when then when you search this one, there is IS specification is there, ASTM specification is there, and ISO is there. Then which one will you follow? IS is more suitable for us. And better you read ISO, then it is more or less the same. More or less the same. And you will get a lot of knowledge, how to handle the sample, which machine you need to use, what speed you need to test, what is a condition, how long you need to precondition this one, the sample, and which atmosphere, whether in desiccator or non-desiccated. All this, it is mentioned. Otherwise, the test is not important. Then we are measuring in what is called despacing. I think you know what is despacing. The despacing in X-ray, we are measuring the despacing. The despacing means you can see that this is a despacing. Despacing means the distance between the clay layer that we can measure using any famous Bragg equation. L lambda is equal to 2d sine theta. So that way we can measure it very easy, very simple. Then you will get that distance. If somebody rubber is fused into that one, the distance will increase. So that way we can check it. Then differential thermal analysis. We are using a lot in rubber technology, polymer technology for designing fire retardant materials, especially for plain mat and other things. When you make a mat for the ordinary household activities, we won't care about the flame retardance of the material. Now it is very important. And in airplanes, this is very important. And airplanes, in the milligram weight increase will add up to the fuel cost. So they won't allow the coating of the material. They were very thin coating, which you need to satisfy the specification. Then we can only do very fine technology with that one. Their cost is not at all a problem. Life is in risk. Whenever life is in risk, cost is not a problem. So remember that one. So we have a differential thermal process where the thermal stability of the material will be enhanced. What happens? How this happens? What is the science in that one? We have rubber. Rubber is easily flammable, burning material. Then you add a nanoclay into that one. The thermal stability increases. How this happens? What is the science in that one? Because science is this one, I will tell you. Sorry. I will tell you I thought, This is a science. This is a science. Okay. See, this is a rubber, and this is a clay layer, and this is a clay layer. Rubber is in between. So in between, what happens? Rubber is wrapped in between clay layers. What is clay? Clay is thermally stable material. Clay pots, clay material, silica, everything is highly thermal resistant material. So highly burning, highly degradable, highly, thermal poor resistance rubber is wrapped in between the clay layers so that the temperature, it won't feel the temperature. That is why the thermal stability will be enhanced. So you can see that one, the testing. Thermal stability, which is a machine used to check this one. Which is a machine, thermal stability for polymeric material, all material, metals. Don't think that I'm a mechanical engineer, I won't listen to this one. This is a polymeric material. But which is a material? Measurement instrument used for thermal stability of polymers materials. TGA. TGA with identical condition. Then I will ask them, what is the condition? Which is the condition you are applying, whether in oxygen atmosphere or nitrogen atmosphere, or both you are using. So don't answer this one, go to the specification. Specification clearly says that up to this one, 400 degrees Celsius, you have to use nitrogen. Then after that, you use oxygen. That specification is clearly telling everything. So without that one, if you're sending your sample to somebody and you are totally unaware of the process and procedures, and copying this to the thesis won't work in actual pictures, actual manufacturing process. And then microscopy, this one, electron microscopy. Can you name some of the electron microscopy? SEM, scanning electron microscopy. Then other one, transmission electron microscopy. What is advantage? What is the difference between these two? Both are used in all type of material research. What is the difference between TEM and SEM? Scanning electron microscopy, it's very simple. It is only analyzing the surface layers to a small micrometer level. Fast moving electrons are hitting the surface, and that depends upon the refracted electrons. They will scatter. Whether the surface is rough, whether the surface has cavities, the material, polymeric material is in contact with the metal or something, the layer formation, but it is totally not giving any picture in the bulk of the material. Then for that one, the ideal picture is TEM, transmission electron microscope. So there what we do, we will slice this one into small nanometer lanes, probably 100 nanometer or 50 nanometer. Then we will hit the electrons. Electrons are passing through that one, not refracting, so that we will get the ideal picture. What is exactly there? So this is ideal technology for checking nanometer formation. And how many of you used the slicing, and anybody used the slicing and scattering of a transmission electron microscope? ഉപയോഗിച്ചിട്ടുണ്ടോ? കണ്ടിട്ടുണ്ടോ? Yes, good. The thing is, if you travel in the road, sometimes in rainy season, there is a small cavity filled with water, and then there is spilled oil is over there. And during sunshine, you can see color pattern. What is the reason? Because that oil layer is in the nanometer range. It can scatter, It can scatter the light. It is of the order of the wavelength of light. And that is the reason. So we are you are splitting your polymer films up to that thickness in a transmission electron microscope, that you can clearly, it is a correct mirror picture of the material. But it is very expensive. And more than that one, there is no good center in India to do this type of work, because cryo cutting is a specialized job. And of course, some centers are doing. And most of the cases, if the slices are not uniform, that portion is dark, and electrons will be absorbed, so you will not get any reflection. So these are the difficulties, this one. And moreover, a good TEM machine will cost around 4 rupees, like a machine. Whereas a SEM machine, I think almost less than a crore. This is 4 crore, 400 lakhs. Then we have infrared spectroscopy. I think that machine you have here, I'm sure. What is the make of the machine? Do you have a infrared spectroscopy machine here? IR? I don't think so. Sony's are, Illa. Okay. It's a very good material chemistry. That all molecular interactions you can find. All molecular interactions. So very good. There is a lot to study in that one. You can have all interactions, whether the polymer is intimate contact with the filler. If so, the peak height and peak width and everything can be measured. Then you can make sure that a simple technique, we have all these techniques. We don't have this translucent electron microscope. All other techniques we have experts also. They will explain everything. And especially this machine is very useful for us for doing reverse engineering of rubber products, plastic products, everything we will do reverse engineering. Use this because if you have a more small rubber, you have the tire with you and take a 10 milligram of the tire part material. What all materials are there? Rubber is there, carbon black is there, oil is there, then some silica is there, some fibrous materials are there. Suppose somebody want to check what is a formulation, that one very difficult because of black material. Do that thermogrammetry. You will get a step like what is called a curve. Every time up to 100 degrees Celsius, all oil will vanish, evaporated off. Then we have it again, we heating up 400 degrees Celsius, all rubber will vanish. Then again, you heat, then will then change the heating medium to oxygen. Rubber will be everything. Then the carbon black will be removed. Then finally, we have a deposit that is inorganic filler. So a good rubber technology can write down the formulation. That way, doing a lot of business in rubber board because that machine is heavily engaged with the 40 plates round the clock running all over the India and abroad. We are getting samples. It's a good technique. And this is a general chemistry. See, then again, very easy. How do you analyze your things? Very simple. Because then there is a two system, immiscible system, intercalator system, and exfoliated system. Now, this is a clay you use. This is a clay, same curve. This is a clay you used XRD's pattern. And the clay has the same d distance. There is a peak. This peak corresponds to the d distance of the clay. Same clay we use. Then we have mixed this clay with some polymeric material. Then again, we are checking the XRD pattern. You can see there is no change. Then initially we have seen the diagram. The clay is just residing as such in the polymer. There is no change. So the polymer, you will get, say, this is a system that you can see that one. See, the layers are there. So there is no change. This is a crystalline material. So there is no change in the crystallinity. So it is giving the same plot. Then in intercalated system, same clay, when you have two type of system, some amount of material will work. Some amount of the polymer will diffuse and some reside acid. So we have a more or less two peaks. And more close to the, that zero, it means layers are separating. The inverse relation between d distance and 2 theta. Then it's exfoliated system, there is no clay at all. Interclay is disturbed. Layers are separated, so there is no peak at all. That way you can very well check whether your material nano is formed or not. And whenever you declare nano material in your thesis or purpose, check this one. This is, I think you understand this one. Then some of the practical work which we did, most of the cases with the, Commercial clay and different type of clay. These are the normal clay, costing around 7 rupees per kg. Bentonite clay, virgin clay, layered silicate, having layer distance without any modifier about 1.224 nanometer, and this is around 0.9 nanometer fluoroheterite. You can see that corresponding to the normal clay blue line, there is no peak. The peak after 10 to theta is not important. Whenever you check the 2 theta, the peak after, the 2 theta beyond 10 should not count. Below that one, you should have to, because the distance only will come in between, below 10 to theta. Otherwise, that other thing is important for some other property. Never take the peak after this one. Okay. And then you check this one. See, this is some artifact. That normal class not supposed to give any peak at all. And then bentonite green one, you have a good peak at 8. And this one, fluoroheterite also has a peak. A lot of and from our analysis, this is a very good material for rubber latex, not for dry rubber. Number. Why? It is not a modified clay. It is a liquid clay. So these are some of the analysis when we do, same way, do the analysis with rubber, you will get a different type of. Make sure that, you did some work, you used the nanomaterials, you got some peak as your previous scholar got. Then declare the same thing as such and repeating the errors or something facts. It's not good. Analyze the things. If you want to repeat this one, repeat it. And then you can see that it will be reflected in your properties also. It must reflect. Then what is so? We declared that nano is formed. Then what is advantage? It must reflect either in your mechanical properties or in barrier properties or in solvent uptake or in thermal stability. Any of these areas, it must reflect your testings. These are some of the 10 electron microscope, that you can see that the rubber is penetrating between the layers. And this is a normal clay without any change, bentonite and fluoroheterite. Then coming to the application level work. These are the things, that which is a rubber used in inner tires of inner tube of tires. Tire is generally made up of natural rubber, polybutadiene, and SBR. And what is that? Inside there is a tube. Now there are tubeless tires where the tube is already fixed with the tire itself. What is that rubber made up of? Butyl. Why? Because butyl only has that much capacity to hold the air inside. If you can make a tube with the natural rubber also, but every day you need to go to the gas filling, air filling. Otherwise, there is molecular level holes will permit the things. That is why your balloon, after inflating, will go down after a day. There's a thing. So if you see the advantage here is you can see that one. Sorry, you can see that the normal clay, that the permeability is very high. Bentonite is medium, and fluoroheterite small addition will come to the level of butyl rubber. So this technology is now using some of the tire companies and in our country. So we have already patented this one also. This is a patent is with us. This is the Indian patent. If you read, you can check this one. You can see, and I think the science why this happens. How this is science is very important. You say how the thermal stability is increasing. What is the science? Because the rubber is wrapped in between the silicon layers, and it's very difficult to heat this one to degrade. So the temperature stability is increased. Whereas in the case of air permeability, the holes are sealed, not fully, in an indirect way, so that it will hinder the travel of gas molecules. That way it is happening. So that is the thing. Then we have a normal organization. You want some rest? Okay. So probably after finishing this one, I will see whenever you do rubber work, you know. Most of the cases, we cannot apply the poisonous rubbery accelerators and sulfur system, especially in small babies products and also healthcare products. There are allergic reactions and also extraction of all organic accelerators or organic materials, very hazardous materials. I think you people are aware of some recent rules in rubber technology that is called REACH, REACH. REACH regulation. REACH regulation. REACH, REACH. Registration, evaluation, and authorization of chemicals. This is not only for rubber. This is true for all exporting material, paint, wood, metal, everything. Now we have to be careful about the REACH regulation. Means there are 253 residual materials you need to check and report. You know that you are adding all these chemicals into rubber and vulcanizing the things at elevated temperature. What happens? Residual materials will be formed, and residual materials again recombining form again problems. And these things are identified in EU, Europe, and they regulated this one. They won't accept any product, this one. So even the mat, even the hose, mat used in their hose, cow mat, they won't allow. Whereas our case, we are using yoga mat, everything with this material. So this is also regulating this one. But go on today itself, check what is REACH, REACH. You have and this 252 material residing poisonous material is not fixed. It is every day, every month they are updating this one. And last year it was only 280. Now it is 252. And every year they are finding new residues, and they have to be. And we have a tester laboratory in rubber boat. We put a new laboratory for this. For checking the export, they won't allow otherwise. Or the gloves exporting the European country, America must certify this. Previously, there are only 2 types of tests for rubber products and most of the products. What are that one? Mechanical test. Mechanical test means a tensile must be 80 to plus or minus 2. Elongation must be 700, something like that. Modulus must be below 5 MPa. And now, later, most of these products they are sterilizing. Means previously gloves are sterilizing. Now they won't allow this one. They are putting this on some probably sterilization, steam sterilization, or some chemical material. Then material must be resistant to high temperature and chemicals. So they are putting a test for that one. This is a chemical test. So our conventional products are, usually we do mechanical test and chemical test. Now the third phase of test came again. That is residual test. Very difficult for the product manufacturer to cope up with this one. And the level is so small, ppm level. And the level is 10 ppm. And you know that there is a particular parameter called polycyclic aromatics in rubber products. There are 18 polycyclic parameters identified. For example, anthracene, naphthalene, then derivative of all these one, pyrene, 1, 2, 3, indene, several things like that. And the total of these 18 parameters, they put as 10 ppm, and every individual component level should not increase above 1 ppm. Check, see how it is impossible to make a product with that one. Then what we need to use? We have to use our edible oil. We are using lot amount of oil in cheap product like rubber mat. And that oil, usually we are using recycled oil. From North India, the used oil, they are recycling, and normal oil, petroleum oil cost around 120, 100 rupees per kg. Why we are adding oil into the rubber? Plasticizer. If you want to put more filler into that one, we want to add more oil. Then only we can, because why we are adding filler? Cost reduction. So these are all interconnected. And previously, a cheap product cannot accommodate virgin oil, we will add recycled oil. What happens? Recycled oil is burned several times, have a lot of polycyclic aromatics, so they will check that Europe and send back. And they put very critical measures, 1 ppm. So we cannot use normal oil, even virgin oil. So we are using soybean oil and other things. So see, the nature is more accommodating now, all these one. Why European Union put such a test there, reach test? Because their environment, their water body, everything is polluted with this type of residual materials, and their infertility rate, cancer, and everything is increasing. So these are all cancer-causing materials. It's 153 identified residual chemicals in rubber products, wood product, tires, textiles, paints, everything they are applying. This is applicable. So we are testing this one. So this is idea. So whenever then we have to remove now we have to remove sulfur vulcanization. We have to change rubber board. So the clients are coming into us. What is idea? How we can change this one? So we have a radiation vulcanization. We have different type of radiation: electron beam radiation, gamma radiation. Previously we were with the gamma radiation, very expensive. Now we have the electron beam radiation, so that we need not want any chemical in that one. Electrons are produced, hit away nitrogens or hydrogens from the hydrocarbon chain, and then fusing these two together, we will get the cross-linked bridge. So things are not so easy. We have to apply identical conditions. You can see that some of the things with here there is no accelerator effect on the clay. You can see that how for this from the gum compound without any filler, this is a stress strain curve. Then you add a China clay into that 110 pHr. There is a small increase in stress. Then to the layered silicate loading and type, it is increasing. So you can select the ideal material. So some of the material properties, tensile strength, and everything is written there. And again, silicate loading. You can see that here what you want to show is, that the gum compound and that the English Indian clay, that is China clay, that in order to get some appreciable level of modulus, if here we are 10 pHr, this green, and then we change this 10 pHr to a same level of what is called a layered silicate. See, almost 3 times increase. And then coming to the fluorohexerite, we have a huge increase. So then you can make sure that nano is formed there. This is idea. So you have to make sure that there is want to satisfy with 1 or 2, 3 changes, the unit change in mechanical. You can declare it as a nano. So I have to be very careful about this one. Then that in India we are producing a lot amount of latex, and we have a Sony record. So this is very important, and this thing is we have to do dispersions with that one. Actually, the natural rubber is made up of rubber dispersed in water. And what is the size of the rubber in that one? Size of rubber particle in water? How much? Approximately average size or range, it is 0.3 to 6 micron, or averagely it is 500 nanometer. So natural rubber lattice is a nanomaterial, nano dispersion, and we are not aware of this one, and we are running all over the world to pick up the right nanomaterial for you and giving dollars. And for 1 gram, you are giving the price of gold. But the natural rubber is a nanomaterial. Natural rubber latex is a nanomaterial, nano dispersed rubber. Small particle, 500 nanometer. And in that one, you are adding your entire bulk fillers and making it useless to convert into conventional products. So what we are adding, there is a ball milling process. We are adding ball milling to zinc oxide. Initial particle size is 40 micron. If you add this into a nanomicron system, natural rubber lattice is 1 to 6 micron. And you are adding a filler into that one, that is 40 micron. So what happens? Entire system will go down. It will settle at the bottom. It will not disperse. So you have to reduce the size by mechanical means, by ball milling technique. That is, so you put the entire thing in a ball and you do grinding 24 hours. 48 hours, slow grinding. We cannot give fast grinding. So that is called ball milling. You can reduce this to up to 20 micron or 10 micron. And sometimes it beyond never go beyond that one because there is a limit which we can go with the mechanical grinding. Below which some certain point, whatever may be the time you are giving, particle never undergo size reduction. That is a normal way. So here we are, what we are using? We are using 2 inch, 1 inch or half-inch steel balls for porcelain balls of materials in the things so that the material will go in between and the grinding and the cascading and it will grind it. But to produce nanomaterials, we have another system, another balls that is called the zirconium balls. Its size is very low and the density is 6. So it is very impact, hitting is over the particle. So it will reduce, it will give you somewhat nanomaterials by mechanical means. But remember that none of the existing mechanical means will not give you a nanomaterial. For that, we need chemical means. So this is a thing, we have this machine there. We have a NADS. Now, the machine here is the NADS machine, and this is a ball used for that one. So now some of the, product making match factories are using this technology for getting what is advantage. We need to add a little amount of the filler so that you will get the more rubbery property and the product rejections are very low. Then we will get very good properties for this one after aging. I said, that there are 4 important properties for a nanomaterial. That is, one is a thermal stability, barrier properties, and then we have a swelling resistance, permeability. These are the things you have to take care of. There should be some several fold increase in any of these materials. Then only we can declare it as a nanomaterial. 2-fold, 3-fold increase, so 2.3 point increase in any of this point should not declare this as a nanomaterial. Should have a X-ray supporting data and property reflection. And you can see that in polyurethane, very important, polyurethane is a polar material, polyurethane lattice. It is separated very well in nanotechnology. You can use, we have intercalated and exfoliated surfaces. You can see that 2 peaks. So that you can make a very good impermeable material for this one. We are using polyurethane latex with the polyurethane with the natural rubber latex for making some of the material because natural rubber latex is non-polar, were very difficult to disperse clay, whereas polar materials can disperse modified clay very easily so that the blend can work very well there. These are some of the very complicated things, the X-ray diffraction, what changes, how this changes, how much happened. So all this indicate that the peaks more close to the zero side will, what is happening, exfoliations are there. You can read that one. These are how the pre-vulcanized rubber is going in between the layered silicates. Again, probably we can stop here, and then nothing is next phase. That whenever you want to do some work with the nanomaterials, what we need to do is go to the Google and check what are the nanomaterials available in the net. And when you do, you can see that 100 varieties of materials suitable for, they are declaring suitable for plastic and rubber. And remember that the plastic technology is entirely different from rubber technology, whereas there is no cross-linking or in plastics, and there is no acceleration system. And most of these, what is called nanomaterials are designed for polymer and is entirely suitable for plastics. In plastics, plastics we are applying heat, adding filler, maybe some photo stabilizers, thermal stabilizers, and then you eject it into the desired shape. There is no cross-linking reaction. And then when you're coming to the rubber, we are cross-linking there. And for cross-linking, we need what is called a sulfur accelerator and initiator, everything. And when you do this one, when you select the right material from there, there is a cross reaction. I said, that You have to select the correct material, otherwise the modifier will interact with your what is called accelerator. So probably when I scanned all these material, there are very few, 1 or 2, 3 materials only suitable for rubber. And I have seen several diseases working with this type of materials and finally end up with the micromolecules declared as nanomaterials. And that is why I am showing this one. So whenever you scan this one, look at the modifier. What is a modifier? Most of them are, they have a modifier in it. And go to the modifier, whether it is a amine pH. What is a pH of that one? Is it amine or a neutral or a acidic? You select the acidic one for rubber. Because if you select the amine, it will act as an accelerator. And it will be sucked out of the clay for the acceleration reaction. And the clay will collapse. So these are things. Then, there are some of the materials which we selected and then we screened this one. Several clays, several types are there. None. Some of them are different type of clays. Some of them are pristine clays, and most 90%, 95% is modified clays. Yeah, mining then modified. Remember? So this modification means to increase the layer distance. For increasing their layer distance, there is a cation inside. They have to cation is positively charged ion. So to interact that cation, they are using basic modifier, probably C10 H19 amine. The amine will go there and interact with the things. What happens? It's an amine. So this amine, all our accelerators are amines. And remember that vulcanization reactions will hinder with acidity will hinder vulcanization reactions, and basicity will increase the vulcanization reactions. That is why all our accelerators are amine derivatives. Amine derivative. You see, TMTD, what is called ZDC, everything is amine derivatives. And if you do the modifier, because of this special reaction between the cation and the modifier amine, and the clay modifier is mainly they are looking for plastic modification. And we are selecting this, wrongly selecting for rubber, but there are some systems good for rubber. That is why most of the nanomaterials are not feeling good with this rubber. See, the thing is, I said, we have the normal clay, organic clay, modifier. This is a modifier because a clay, there is a cation inside, interstitial cations. You have to fuse something bulky molecule with the cation, then only the clay will be separated. For that one, we are using this type of material. And see this amine. This amine is good for here, but it is oppositely working with the acceleration reactions. So the gallery space increase the compatibility. That is why you are using this one. And then modifier higher properties are with the increased chain strength. So means if you are using this chain strength very high, very long, you have long, but it's called bigger size. So your properties will be high. The cation, smaller the size of the interstitial cation, higher the property. So these are all basic materials, basic things. But whenever you coming to the application level work, these are very important. That is why I'm again showing this one. We will see the application level work probably after the T. Then see, I said, that the thing is how the layer distance are increasing with the modifiers. You can see that one. This is the modified. So I said, this modifier must be acidic for rubber. So these are all something like basic. So there is a one, can you analyze a good chemist, I think, can tell you one material is good for rubber. Can you tell me that one? You can simply look. And if you know the valency and other things, you can, one is good. What is that one? Here, all this based on these amines are, this modifier is based on nitrogen, and the valency of nitrogen is 3. And you can see this one. There is no modifier. This is dimethyl benzene. So what has happened? 3 of the valence is used, nitrogen 3 of valence is used. So dimethyl to methylamine, one benzyl, hydrogenated tallow, that is a molecule. So probably I think dimethyl benzyl hydrogenated tallow. There's a continuous word, so 3 valency. So this is an amine. Still it is an amine. See here methyl dihydrogenated tallow. 1 methyl, 2 di. So again 3 valencies are used. Here we can see dimethyl dihydrogenated tallow. 4 valencies are used, and there is only 3 valency for nitrogen. So nitrogen becomes acidic. So that clay is good for us. This is the idea behind that one. So we proved this one with our work, and most of the cases we have to screen this one. And then some of the cases, I know that we cannot satisfy all this one. We want what is called nanomaterials for getting property advancement, where we cannot use sulfur vulcanization most of the cases. Then we have to shift from sulfur vulcanization to peroxide vulcanization. What is peroxide vulcanization? There is no accelerator. The clay will work there, no problem. And you can see that you see what happens. See, same clay. I will tell you this one. This blue line, this is for the peroxide, and this is for the same clay in rubber system with sulfur. So it is acting more or less in a limited manner. So you will get a microcomposite here. See, even with the layer distance, there is no advancement in big advancement. You see, peroxide, it is working very well. And you can see how much is the variation there. See, it is going up and down with the peroxide system. See that this is a sulfur. 1 point here, 1 is here, 1. So some of the systems are working, some of them not working. This is the reason. So you have to be very careful by selecting clay. Either you cannot work with the particular, you have to select, if you want to select a particular clay and it is not suitable for sulfur, then shift it to the peroxide. Then a big chapter, another big one, it's all are related to the what is called our real manufacturing sector. Probably I don't know whether you are boring or not. If you're interesting, okay, ask some questions, then I know how much you are grasping. I can orient like that. Okay. Coffee.
Yes. Now it's time for a tea break, and we will resume the session at 11:15. ഇപ്പൊ സ്റ്റേഡിയം വെച്ചു അപ്പൊ നമ്മള് ശരി അതെ 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 അതെന്താണ്
Especially time for the
Now we shall resume the session. Over to you, sir.
Okay, shall we start? See, then we have, I said, we are using zinc oxide in low amount in rubber technology. Zinc oxide is an activator. I think, whenever you write formulation, write rubber technology, we are adding 5 parts per 100 parts of rubber. It is very high. And there is some disadvantage with the zinc oxide. Zinc oxide is a highly dense material, and it is now considered as a heavy material. And it is a lot amount through rubber products is going to the effluent, to the water stream and the environment. And it is not good for aquatic species. So we have restrictions for using zinc oxide. You know this one? Whenever you have a rubber factory making gloves here, St. Mary's nearby, they are using zinc oxide dispersion. And whenever the finished product, they are leaching in water to control the residual activity, residual chemicals. And it is true for all products. Most of the lattice products, they are washing their product to reduce the residual proteins and chemicals. Otherwise, the product never pass the strength and measurements. So the simple technique is wash this one in a warm water, either online washing or offline washing. And then previously there was no problem for washing this one. Now, when you wash this one and release the water to the environment is difficult. And releasing some amount of the material, they will check it, BOD, COD and other things. And releasing zinc oxide is difficult now, it is banned. So if the zinc oxide content in the effluent is low, then it's okay. But now we are using every 100 parts of rubber, we are using 5 parts of, or 2.5 parts, or sometimes 2 parts of zinc oxide. And then half of this will be react in the product, and half, most of the things are coming to the effluent. And we are placing this to the water and causing problem to the environment. So we cannot avoid zinc oxide in our normal formulations because it is an activator for sulfur vulcanization, especially for lattice products. And then how can we reduce the solve this problem? This was one of our project, and we applied nanotechnology here, and it was successfully designed, and we are giving 4 critical products these type of things. Then all of a sudden some rubber mat making people will ask, can we adopt this technology? Can we give this one? Because this is only for washing wherever products are washing. Lattice products to remove the residual materials. There is offline and online washing is recommended. But as in the case of a normal doormat or rubber mat or tire, there is no washing. So nothing is going out of this one. So it is not recommended. So this is recommended only for latex products. And then you can see that one, nano dispersions, they are very fine and they excellent film properties because the rejections are very high. Very important whenever you do some manufacturing process, the rejection percentage is very important. If it is a rejection percentage is very high, then that will affect the factory. So we have to reduce this one. And again, particle size, low dose, residual chemical activity, environmentally friendly. These are the things we are looking for whenever we project a nanomaterial dispersions. Here also, we are not recommending nano zinc oxide. Why? Nano zinc oxide is hazardous. We are recommending it as a dispersion. Then we use then we look into the history of zinc oxide. You can see it is all as a red seal. Previously, years back, it appeared as red seal, white powder, very high particle size, so 300 to 400 micron size. And then we will ball mill this one. Then later we have go to white seal, where 90% is below 40 micron. Then we have came active zinc oxide. So you can see that we have almost 90% is below 15 micron. So our purpose is to reduce the particle size and to also reduce the dose. When you can reduce the particle size, suppose area big, so you can reduce the amount of the material. So and finally, nano. So you can see that all these areas, what we are doing is a particle size reduction. So particle size, we have seen how it is related. Three particle, then 300 particles, then 3 million particles, like that is going on. When you tenfold reduction in particle size, the effectiveness, the area available for surface is very high. So that way we are reducing this one. See, I will tell you the things. You have a look here. It's very interesting slide. You can see what is a real science of nanotechnology. You can see that one. Whenever you have that a particle with a 1 nanometer size, 1 nanometer size, there is atoms inside, and atoms are of the order of Armstrong unit. So the total atoms may be, depending upon the material, maybe 10, and the atoms at the surface is 8, and the percentage at the surface is 80%. So why we are only looking for the atoms at the surface? There is atoms at the bulk also, because atoms at the surface is initially more, friendly, more in front of reactions. So that is why we are counting that one. Then, see, you can see that when the particle size is very high, the atoms at the surface is very low, 0.2. When you reduce this one to 1 nanometer, 80% of the material is in the surface. So that is the idea, to reduce a particle size, and that way we can reduce a total dose of material. I think you got the point. Then smaller the diameter, higher the atoms at the surface, and greater the activity. That is important. Then I said, how to make this one. It's a nice machine for making nano dispersions with the zinc oxide. We are using zirconium balls of 200 micron size. Then we have a very, very small, what is called a particle size. So this is a machine we are using. And then every time we will checking the particle size. And there are two types of particle size, micro size analyzer and nano size analyzer. So whenever you go for particle size analyzer for nanomaterials, ask specifically for nano size analyzer. Otherwise, they will check your particle with the micro size. You will definitely get values. And the people evaluating your thesis will understand this one. And it may be embarrassing for you. So maybe they will ask some questions also the final stage. So whenever you ask focus, check whether nano size analyzer, whether the center has a nano size analyzer. Then what we found is, when we check this one, with mechanical means, we found that none of the material we can achieve the real nano size with the mechanical means, because here we are using simple grinding with the small balls at very high speed, and lot of processes are there, and pumping water and other things. And then, of course, we can reach only up to 500 nanometer or 600 nanometer, not beyond that one. And real nano, previously explained, was come to 100 nanometer. So then we changed this to chemical process. Probably it is may not be digestive for the most of the people sitting, but there is a process from urea. We will check it, and we will get nano zinc oxide. Only by chemical process we can make a nano material, and even every chemical process we can make any nano material. But the problem there is, at the right time we have to interfere with surfactants to avoid agglomeration. Nanomaterials are atoms size materials. See, 10 atoms, almost the size of a molecule items. They are very reactive. They will couple together, combine together, agglomerate. So you have to avoid that one by masking the surface with some agents, repelling each other. So that is the same technology in rubber latex. How the lattice is stable. If you look into the science, rubber particle, very nano size, they will agglomerate, but they can't, because there is proteins are attached to its surface. Tree is making that wonderful science for the latex, so they cannot come back. They repel each other. So the same case, we are adding different SDS or different type of surfactants. We will get the nano size zinc oxide, and you can see that different. See, this is a surfactants we use, the SLS and the things. You can see we have almost achieved 100 nanometer size here with the particle size, and not fully, but still it's good. Then we will check this in a what is a formulation, gloves formulation, surgical glove formulation. You can see that with this one we are only removing zinc oxide with the nano zinc oxide and normal zinc oxide. Normal zinc oxide 50 pSr and nano zinc oxide 10 pSr. See, 10 times, almost 5 times reduction in zinc oxide loss. And you can see that we are in very low amount also here. Then all other properties are similar. We can then go to see in a glove formulation, how much is hazardous chemicals we are adding. Natural rubber latex is a pure environmentally friendly natural material. You are adding lot of chemical into that to make a useful product. And then finally, we are checking the residual chemicals to make it, in the real service process. So these are the things. They are all very poisonous, and they have their own inherent hazardous nature. And then by heating, they decompose, and some of the things union again to them, producing more dangerous materials. And then you can see that. Everything, the properties, you can see that the tensile strength, the micro, nano level 1 and nano level 2. See the tensile strength for the micro zinc oxide and nano level 1, nano level 2 means we are adding only 0.115 amount of zinc oxide. Still, we are getting good properties, tensile and tire strength. This is we are measuring with the machines. We are calibrated machines. Then see the modulus. What is modulus? What is tensile? Difference between tensile strength and modulus? Both are forces. Modulus at the breaking point is called a tensile strength. And for a particular property material, there are only one tensile strength and several modulus. Modulus at 10%, 20%, 30%. Like that, till the breaking point, maybe 1,000 times, you have several modulus. And modulus, it is found that modulus as 100% is very important for gloves. Why? Because when the surgeon put his gloves over this one, he keep this size in the hand always this way. If it is a modulus is very high, the gloves will strain his hand, and a surgery lasting for 14 hours may impart pain on his hand. So that is why this property is being measured. You have to keep the original shape of the, surgeons. So that is a property more closely related with this particular behavior. So we are checking that one. So every property, so not simply checking the property is related to service behavior. Remember that one. Okay. Then see, we have several results regarding this nanomaterial, but I'm not giving all the things. See, our final properties without affecting the product properties. We have to, reduce the zinc oxide amount. Like that, we have to reduce the effluent. Like that, that most of the properties, if the effluent amount is very high, then you won't get a pollution control license and rubber board license. For starting that one, we have to say feasibility. We have to give feasibility report. We are giving project report and feasibility report for factories. And that is essential for starting a factory. And if you don't have a technology for making this one, we, being the authority, the official body can't make a factory project report. So we designed this one, we achieved the level. You can see that the conventional things, if you are making a micro distillation, normal zinc oxide, the effluent may contain around 700, 700 ppm of zinc oxide in the effluent. And if you nano level 1 and level 2 is a very low detectable level of nano zinc oxide. What we did is, reduce the size, increase the activity, and total amount reduction without affecting the properties. This is achieved. Then we can see what are the applications, major applications of rubber nanocomposite. Probably the last sector of our speech. You can see mainly packaging applications. That is soft drinks, beer, food, pharmaceutical, electronics, automobile components. In some of the things, when you, especially nuts and other things, when you pack it, you can see that the air is sucked out of the what is called the packet, right? That air causes it. This is seeds contains, especially nuts and other contains essential oils. Most of them are unsaturated. In presence of air, it undergoes saturation. That is called tanikum. കേട്ടിട്ടില്ലേ? അതുകൊണ്ടായിരിക്കാൻ air suck ചെയ്തത്. So that is fast in the in presence of air. But still, there are recommendations. Some of the that is called modern packaging material. You have to there is no penetration of oxygen through the packets, so we can use these materials, nano material for packing materials. And again, beer and did you see that how many I think you are consuming bottled, can bottled foodstuffs? There is a rubber part. Did you see all can sealed food, soft drinks, beer, and everything? There is 2 parts. Rubber is used. Can you tell me where is it? This one, rubber parts, all seals. You can see. And the top, there is in the top, there is a, curled, that the 2 parts are already winded together. And in the bottom also, these cans are made up of 3 metal sheets, top one, bottom one, and the horizontal part. After filling this one, mechanically, they will seal the all parts, mechanical joints. Then if it is, of course, mechanically very nicely joined, but still there is, seepage of the, food through the things, or seepage of the oxygen through that one, causing bacterial infection and other things, foodstuffs. Maybe you recommend 1 year, 2 year, it will be spoiled within days. So to seal that one, before sealing the mechanical joints, they will spray what is called the latex rubber solutions. Then they will bind. So the entire cavity will be sealed fully, and some of the things are contains nanomaterials also. And even the washing machine, that the washing machine, there is nano, that where is a washing machine nanomaterial is imparted? Can you tell me? Our normal washing machine. There is a small bag collecting tint and that other things in the washing machine. If usually you open that one, there's a small basket and you will clean it. But sometimes this is very foul smell. Maybe if you are regularly not cleaning, it is foul smell. Now the modern machine do not have that foul smell. Why? Because this is nano zinc oxide embedded in that one. So there is no bacterial action in that one. So that's the reason again. So wherever there, cases, barrier properties are required, we can use this one. Antibacterial properties are required, you can use nanotechnology, barrier, anti and reinforcement. Everywhere we need this nanotechnology. And again, in now we have the EV machines, EV electronic, this electric vehicles, EV, and where we need to reduce the weight of the metal parts. And then what happens? Most of the metal parts are replaced by, that polyamine reinforced or epoxy reinforced silica materials, which is more stronger than steel and stable than steel. So in that one, automobile components, we are using this one. And then the market is more towards, huge market is, the trend also shows that there is a huge market, growth for this one, for the nanomaterials of different types. Then we can see some of the nanomaterials successfully. We are giving recommendation for this one. I know that mainly, see, you can the nanofil SC 3000 is used as a halogen-free fire retarder. Where is the use? Know that all rubber is highly flammable, highly burning materials. The fire hazards, tire factory, everything, that. Suppose this is with the vehicles, this is very, very severe. And in some plane, that airplane applications, all rubber parts. We cannot avoid rubber parts, but rubber parts must be not, fire retardant materials. And for that, usually conventionally we are using aluminum trihydrate where we need to use around 100 parts, or even, antimony trichloride. So antimony trichloride is a very good material, very costly, but there is a problem. It contains halogen. What is the problem with halogen? Why people are, you are using chlorine for water purification, then, we are very conscious about the halogen material in rubber. Why? What is the reason? Now PVC, polyvinyl chloride is, that is denied, banned in most of the developed countries. What is the reason? And polyurethane material is banned. Reason for firefighting is hinted, that hydrogen cyanide is liberated in polyurethane burning. PVC liberates HCl, and here also chlorine. So firefighting and other things are very difficult. So they banned this one. So we are using this one nano EC 3000. Of course, very costly material, but the dose is 1 to 2% only. So we are recommending this one. We are already given formulations. Then conventional, see, I said, conventional flame retardant, if you get that much level, we introduce 50 to 65%. And it will give you improved properties also. Then flame retardants, I said, then for, transparency, the thing is, most of the cases we need sometimes more transparent than glass. Some of the product, hidden cameras. You cannot see the camera, sometimes, if you want to do something, you will look, there is a camera or not. If there is a camera, we all behave very nicely. But some of the things, even though it is exposed, you cannot catch it because it is transparent. So here, some of the things are body is made up of this glass like polymeric nanomaterials. There's 40%, it has 40% reduction in water permeability and highly transparent. Then a lot of biomaterials are used, biofibers are used. See the soybean stalk, wood pulp, sugar beet pulp, potato pulp. These are all being used. Several applications are there. These are scaffold. That when you have an injury with a nerve or brain, it is irreparable because cells are not growing. Why it is growing? It has no support. And if you can give a scaffold support on that one, it will grow. So there are recommendations. So this is not from rubber board. This is a normal, nano material, nanofiber is applications. A lot of applications are. There is a company doing all this business in US. That is InMat company. I visited this one for rubber applications. So they are doing all these type of materials. Some of the Chinese medicine, findings they are using very nicely in nano with the nano materials, wound healing. And then wound, again, it is a titanium foam, bioactive nanofiber in bone regeneration. Not if previously we are using calcium phosphate. It has very high absorption of moisture, artificial bone. See that this is a barrier properties, that InMat Corporation, this is a USA company I mentioned, barrier coating with NR. You see, you are using natural rubber that could provide same barrier as currently used butyl inner tubes at a lower cost and weight. So this is a material. You can see it's 1 to 2% of this particular material that is some layered silicate, then coating over the tire will give you same level of what is called impermeability with the product. This is a material, vermiculite, the dispersion, that is a particular clay with a very high aspect ratio. These are the some of its peculiar properties. This material is very dense. 1% is a 1% solution, very thick. Because what is the advantage? That is an indication of nano formation. You're telling that some companies advertising some nano dispersions good for rubber is available with us. Price is very high. It will give you good properties. And then you'll ask how much is a solid content in it. These are 10%. Will you buy this one? 10% means it is not nano. We cannot add 10% in a nano material. In 1%, 5%, 2%, 3% is ideal. So people without knowing this will buy with this one. But 10% is a micro material, not nano material. The solid content is low, very viscous nature, and transparency. What is transparency? That is giving the nano dimensions. It's the thickness is of the order of the wavelength of light. So it is transparent. This is transparent, highly thick. So with the physical appearance itself indicate that the product is a nano. So you have to judicially select this one for your applications. Then tires, I said, protective gloves wherever we can use, where we need barrier protection for pathogens, bacteria, virus, and other things, where the normal glove won't work there. Nipah virus is very small, not the conventional one. So doctors may put sometimes 2 gloves or 3 gloves, but may not work there. So, but with some type of nanomaterial, with the natural rubber, with the single use can use. This is a recommendation. See, again, chemical protections, that anyway, it won't allow gases to pass through the material, or it will take a long time. So we can even, it's a mask made up of this one, can be used for against, that in oil fields or in army or wherever hazardous gases are involved. You can use this one. So some of these findings we are also collaborating with the DRDO for making this type of materials. Rubber mask inside there, we are putting some layer of nanomaterials. See, they can see that current market in the InMat technology, sports balls, the bounce and feel of natural rubber with the retention of butyl. Wilson double core ball, the official ball of Davis Cup is made up of natural rubber nanotechnology. It is marketing now. So this Davis Cup wall, that is we need a very high level of air retention. That is why the players are checking this one against throwing against the ground for every strike. So then only they know where they need to hit it and what force they want to strike it. So they're checking that one. So this is a value-added material. Again, air retention without weight, rolling resistance, and cost penalties of butyl rubber inner liners. So we are using all these one in applications. recommendations are there. And then whenever you use nanomaterials in polymers, you can see where the polymer will stand, what is the performance, oxygen index, and everything. You can see even the NR is also very good for if you make normal natural rubber is impermeable to air, highly burning, low thermal degradation, very fast degradation thermal. When you convert this into nano, it will be resistant to permeation, highly thermal resistance, or fire resistance. These are the advantages. So you can select the application accordingly. These are some of the commercial, rubber and plastics performance with the nanomaterials. And you can see that these are some of the applications for cryogenic storage tank, especially barrier coatings. You know that the bag even made up of starch with the nanomaterial coating can hold water for even 3 days. It will normally starch will dissolve in water, so it can hold water for 3 days. But so again there is cylinder, storage tanks of helium. That whenever we for airspace application, this helium hydrogen need to carry as a fuel, but the very leaking is very high. They cannot carry metallic containers to space because mass is a constraint. So use polymer. Whenever you use polymer, seepage or leaking is very high. So they are using this one. So they have 80% reduction with the gas. That is, I think we will finish here. And if you want to ask some questions or something, anything you can ask, no problem. If I know, I will give you regarding rubber, or my favorite area is specifications, testing, and development. Thank you very much.